Presenting some questions from chapter 22 about Gauss's law. So for our first question, we have the question: a conductor with an inner cavity like that shown in figure 22.23c carries a total charge of 4.6 nanocoulombs. The charge within the cavity insulated from the conductor is negative 6.10 nanocoulombs. How much is the charge on A, the inner surface of the conductor, and B, the outer surface of the conductor? So first, let us take a look at our given. For our total charge, we have again 4.6 nanocoulombs. And for the charge inside, we have negative 6.10 nanocoulombs. And this question is relatively easy if we remember the fact that the inside of a Gaussian surface must be equal to 0. So to have a negative on the inside, it must be negated by an equally positive charge. So the charge overall on the inside is equal to 0. So first, let us look into this Gaussian surface with the charges placed already. So as you can see, the negative charge is being negated by the positive charges that have coalesced around it. This is because the negative charge has attracted the positive charge, creating a net zero electric field in that area. So if we look into our formula, we have the formula of negative 6.10 nanocoulombs, which is the charge inside, plus x is equal to 0 because we want that the field inside is equal to 0. So by a simple transmutation, we find out that x is equal to 6.10 nanocoulombs. This is the charge of the inner surface of the conductor. However, as we know, these charges do not come from anywhere, so these positive charges must have come from somewhere. So from here we can infer that these positive charges came from the outer surface of the conductor, therefore decreasing the amount of potential positive charges and causing the total charge to decrease to a negative state. So let us look into a new formula that we can use to find the charge of the outer surface of the conductor. So as we can see, the charge outside is equal to the original charge outside, which is 4.6 nanocoulombs, minus the charge that was taken out to be able to negate the charge in the inside, which is 6.10 nanocoulombs. So 4.6 nanocoulombs, the total charge, minus 6.10 nanocoulombs, the charge in the inner surface of the conductor, is equal to negative 1.5 nanocoulombs. So as we can see, that due to this negative charge inside the Gaussian surface, the total charge of the outer surface of the conductor becomes a negative value, while the charge of the inner surface of the conductor is equal to a positive value to be able to negate the inside of this Gaussian surface. For our next question, we have the question: how many excess electrons must be added to an isolated spherical conductor of 40 cm in diameter to produce an electric field of magnitude 1170 newtons per coulomb just outside the surface? Well, first, what is our given? First, our radius is equal to 20 cm. How did we get to this? Well, given is diameter. So as we know, 2 radii is equal to 1 diameter. So all we need to do is to divide 40 by 2 to get our radius, which is 20 centimeters. Next, our electric field is 1170 newtons per coulomb. To be able to find the amount of excess electrons that is needed to produce this type of electric field, we first need to find out the charge that is needed. So to find the charge, all we need to do is to use the formula to find the electric field, which is E is equal to kq over r squared. Through this, we can derive our equation to find Q as Q is equal to ER squared over K. All we needed to do was to multiply R squared by E and divide it by K to be able to get Q. So first, we substitute our values. So for K, for E, we substitute the 1170 newtons per coulomb multiplied to our radius squared. So for 20 cm, we can translate it to meters, which is 0.2. So multiply to 0.2 squared divided by K, which has a value of 9 times 10 to the 9th newtons m squared over c squared. After inputting this value, we'll end up with a charge of positive 5.2 times 10 to the negative 9 coulombs, or 5.2 nanocoulombs. Next, we can use our second equation, which is Q is equal to Ne, also known as charge is equal to the number of electrons multiplied to the charge of the electron. From this equation, we can derive our equation with n being the number of electrons is equal to charge over the total charge over the charge of a single electron. So from this, we can put in our equation as n is equal to 5.2 times 10 to the negative 9 coulombs over 1.6 times 10 to the negative 19 coulombs. 1.6 times 10 to the negative 19 coulombs is a constant value for the charge of one electron. After dividing, we'll end up with n is equal to 3.25 times 10 to the 10th amount of electrons. For our final question, we have the question: the electric field at a distance of 0.124 meters from the surface of a solid insulating sphere with a radius of 0.366 meters is 1,690 newtons per coulomb. Assuming A, that the sphere's charge is uniformly distributed, what is the charge density inside of it? And B, calculate the electric field of the sphere at a distance of 0.217 meters from the center. So first, we may solve for the density of the sphere. So we'll use the formula for density, which is P over Q is equal to Q over V, with P representing density, Q representing the charge, and V representing the volume of the sphere. So we know that the volume of the sphere is equal to 4 pi r cubed over 3, with r representing the radius of the sphere. Next, we need to find the distance between the center of the sphere and the edge of the electric field. So since this electric field is outside the sphere, we know that this distance is larger than r. And since we are given the distance from the edge of the sphere to the edge of the electric field, to find this distance, all we need to do is to add the radius to the distance of the electric field from the surface of the sphere. So 0.366 plus 0.124 is equal to 0.490. So this is the value of small r, or the distance from the center to the edge of the electric field. Next, we can use the formula, which is EA is equal to Q over E naught. So this E represents the electric field, A represents the area, Q represents the charge, and E naught represents the constant, which is 8.85 times 10 to the negative 12th. So since we are trying to find Q, because we are able to use this Q and substitute it to our previous equation, which is the P is equal to Q over V. Q, which can be derived from our equation of EA is equal to Q over E naught, is equal to E naught times EA. So after this, we can substitute E naught times EA into the numerator of the original equation of P is equal to Q over V. So we end up with the equation of P is equal to E naught times E times A over 4 pi over 3 multiplied to R cubed. Afterwards, A, which is the area, can be surface area, which can be turned into 4 pi r squared. So we end up with 4 pi r squared multiplied to E naught and the electric field divided by 4 pi over 3 multiplied to the radius cubed. And our final equation, after removing the common factors in the numerator and denominator, is equal to E naught multiplied to E r squared over r cubed over 3, with r on the numerator representing the distance between the center of the sphere and the edge of the electric field, and the r at the denominator representing the radius of the sphere. Afterwards, all we need to do is to substitute. So for E naught, we have 8.85 times 10 to the negative 12 coulomb squared over newtons times meter squared, multiplied to our electric field, which is 1,619 newtons over coulomb, multiplied to our radius, to our distance squared, which is 0.490 meters squared, divided by our radius cubed, which is 0.366 cubed, divided by 3. After substituting, we end up with a final final density of 2.2 times 10 to the negative 7 coulombs, with our microcoulombs being 0.22 microcoulombs. Next, we can calculate the electric field inside the sphere at a distance of 0.217 meters from the center. So we can use a formula to calculate the Gaussian surface, which is E is equal to 1 over 4 pi E naught multiplied to Q enclosed over R squared. From this, we can also use the second formula, which is the Q enclosed is equal to density times V. Remember, we already solved density, and V, which is the volume, can simply be found by having the volume of the sphere being 4 pi over 3 multiplied by r cubed. So all we need to do is to substitute PV into Q enclosed. So we end up with the final equation of 1 over 4 pi E naught is multiplied to P times 4 pi over 3 r cubed over r squared. After taking out the common factors in the numerator and denominator, we end up with the electric field is equal to Rp over 3E naught, with R representing the distance from the center to the end of the electric field, P representing the density, and E naught representing the constant, which is 8.85 times 10 to the negative 12 nanocoulombs. Finally, we can substitute our factors and we'll end up with E is equal to 0.217 meters multiplied to 0.22 microcoulombs over meters cubed divided by 3 times 8.85 times 10 to the negative 12 divided by newtons meter squared. After this, we end up with our final size of the electric field, which is 1,798 newtons per coulomb. So this was the final question for chapter 22. Thank you for listening, and I hope to see you more in chapter 23 when we discuss more about the electric potential. Thank you.